Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So we start our chapter 1, which is the introduction with Surah Al-Fatihah. Ya, sure. Amin, amin ya rabbal alamin. So we continue our topics. Okay, so previous topics I have give an introduction of overview of the subject. So today we will go for first chapter, which is the introduction for power generation, transmission and distribution. Okay, this is the contents of chapter 1, which is the introduction. First, we will go into the importance of electrical energy. Okay, so we will know about the energy, the electrical energy, why it is superior to all other forms of energy. Okay, and then after that, we'll cover the history, a little bit of history of electricity power system. Okay, when the electricity power system started, which is 1882 and so on. Okay, after that, we'll cover the modern electric power system. So you will know on what is the components of the modern electric power system. Then we'll go to the units of energy, and also finally is the efficiency. Okay, so first is the importance of electrical energy. Okay, so energy may be needed as heat, as light, as motive power, and etc. Okay, the present day advancement in science and technology has made it possible to convert the electrical energy into any desired form. Okay, so the electrical energy is superior to all other forms of energy due to the following reasons. So first is because electrical energy is in a convenient form. Electrical energy is a very convenient form of energy. Okay, it can be easily converted into other forms of energy. For example, if we want to convert the electrical energy into heat, the only thing to be done is to pass the electrical current through a wire of high resistance. Okay, and then similarly, electrical energy also can be converted into light. Example like the electric bulb, and also the mechanical energy, for instance, the electric motors. And then electrical energy also is easy to control. The electrically operated machines have simple and convenient starting, control and also to operate. For instance, an electric motor, we can start and also stop the electric motor by turning on or off with only using a switch. Okay. Similarly, with simple arrangements, the speed of the electric motor also can be easily varied over the desired range. Okay, it's very easy to control. And then the third one is greater flexibility. One important reason for preferring electrical energy is the flexibility that it offers. It can be easily transported from one place to another with the help only using the conductors. So very, very flexible. The fourth one is the cleanliness. Okay, cleanliness. Electric energy is not associated with any smoke, fumes, or poisonous gases. Therefore, it is used ensures cleanliness and healthy conditions. Okay. Okay, you look on to the next an overview of the history of electrical power system. Okay, so you look here, this is just a timeline starting from 1882 until 1888. So, on the history on how the electrical power system started. Okay, so on 1882, Thomas A. Edison opens first street station, New York City. He has developed the waterway-driven DC generator installed in Appleton, Wisconsin. Okay, and then 1882, 1884, Frank J. Sperrett produced DC motor for Edison companies, and then 1885, William Stanley develops commercially practical transformers, and 1888, Nikola Tesla introduced two-phase AC induction and synchronous motors. Okay, this is on how the history, what is the history of the electric power system started. Okay, then we go to the modern electric power system. So what is the modern electric power system? So this electric power system have four main components, which are the generation, the transmission and substation, the distribution, and also the loads. So these four components will contribute to the modern electric power system here. Okay, you can see here, this is the generation. Okay, so we have the three-phase alternator or the generation, and then we have the step-up transformer. Okay, from 11 kV go to 132 kV. Okay, so we have here, this is the transmission line. So we have the transmission line and also the sub-transmission line. And then after that, okay, we go to the step-down transformer. So step-down transformer, we have here is the transmission main intake. Okay, transmission main intake or the PMU, pencawang masuk utama. Okay, so it will step down from 132 kV to 33 kV. Okay, in this case. And then we goes to the down here is the distribution side. Okay, so we have the generation part, we have the transmission part, and we have the distribution components. So distribution components we have here is the main distribution substation or pencawang pengagihan utama. Okay, and then we goes to the after that we goes to the loads. Okay, this one is the load. So either residential, commercial is the types of the loads that will be supply the electricity to. Okay, so we have 400 volts for the three-phase loads, and then we have the single phase, which is 230 volt. Okay, this is the overview of the modern electric power system, which consists of the first one is the generations. Okay, we have the generations, and then goes to the transmissions, and then go to the distributions part. Okay, and then finally is the load. Okay, so this is the modern electric power system. So this figure shows types of distribution systems. You can see here from generation, transmission, and go to the distribution part. You can see there's a large industrial load, industrial or large commercial load, and also the residential or rural area for load. Okay, first we go to the generation system. So when we talk about the generation, it's compulsory must have generators, which are the three-phase AC synchronous generator, or we call the alternator. Okay. So the synchronous generator or alternator is an electrical machine that converts the mechanical power from a prime mover into an AC electrical power at a particular voltage and frequency. The synchronous motor always runs at a constant speed called synchronous speed. Okay, so basically the synchronous generator have two rotating fields, which are the rotor and also the stator. So this one is the stator and this one is the rotor. So the stator is the stationary part of the AC motor, while the rotor is the rotating electrical component. So this rotor is located inside the stator and is mounted on the AC motor's shaft. Okay. So basically, these generators have different types of size, depends on the generating station, either between 50 megawatt to 1,500 megawatt. Okay. So energy is available in various forms from different natural sources such as pressure, heat of water, chemical energy of fuels, nuclear energy of radioactive substances, and etc. So all these forms of energy can be converted into electrical energy by the use of suitable arrangement. So if you look at here, we have, for example, this one is energy. Okay, energy from some sources. So we have here is the prime mover, and then goes to the AC synchronous generator, and then it will produce the electricity. Okay. So the arrangement essentially employs, as you can see in this figure, an AC synchronous generator. We couple it with a prime mover. So prime mover is driven by the energy obtained from various sources such as burning of fuel, pressure of water, force of wind, and etc. Okay. So you can see here, for example, we have the energy from sources of chemical energy of a fuel, for example, coal. Okay, it can produce steam at high temperature and pressure. Okay, so and then it will produce the steam. Okay, the steam is fed into a prime mover, which may be a steam engine or the steam turbine. Okay, so the prime mover is this, for example, a steam turbine. So the turbine converts heat energy of the steam into mechanical energy, which is further converted into the electrical energy by the AC synchronous generator. Okay, for the prime mover that use the steam or gas turbines, it will produce high speeds around 1,800 to 3,600 revolution per minute RPM. Okay, if use the hydraulic turbines, we produce low speed 150 to 300 RPM. Okay, so this is the power station available in Peninsular Malaysia. So we have gas turbine, steam turbine, copper cycle, and also etc. This one is the major generation station in Sabah, and while this one is a major generation station in Sarawak. So generation capacity in Malaysia in 2014 consists of 30,875.23 megawatt, which consists of the natural gas about 47%, And then we have coal 24%, hydro 15%, diesel, natural gas, biogas, solar, and etc. Okay, so you can see here, solar, which is the renewable energy, is in 2014 is only 0.55%, and I believe in 2020 it has been increased. Okay, and then we look at next is the transformers. Okay, so we have the step down and also the step up transformers. Step up transformers are used to increase the voltage level for long distances power transmission. So in modern utility system, the power may undergo 4 or 5 transformations between the generators and the ultimate user. Okay, so if you look at here, this is the overview of the modern electricity power system. So we start here with the generation. Okay, so we have the generation here. Okay, then we go for the step up transformer. Okay, and then here we have next, and then we have one more. Then we have here one more transformer, and then go to the loads. Okay, so starting from the generation normally is about 11 kV, and then go to the step up transformer. Transformer is around 11 to 132 kV. Okay, and then we have the transmission line here. Okay, this one is the transmission line. Okay, and then we have here is the pencawang masuk utama or the transmission main intake. Okay, normally here is 132 to 33 kilovolt. Okay, so here we have the sub transmission line, and then we have here is the PPU. Okay, PPU or pencawang pengagihan utama or main distribution substation. Okay, and then from here we have the pencawang elektrik or the distribution substation, and go to the loads. So loads consists of 400 volt for 3 phase, and second we have 230 volt for single phase. So you can see here we have 4 transformation. Okay, this one 1, 2, 3, and 4. So we have 4 transformations between the generation until the load. So 4 transformations. Okay. So next we look on to the transmission. So transmission basically is used purposely to transfer the electric energy from generating units at various locations to the distribution system. The transfer of power between regions during emergencies, and then in Malaysia, the transmission voltage are standardized at 132 kV, 275 kV, and 500 kV line to line. So sub-transmission connects the high voltage substation through the step-down transformers and to the distribution substation as I mentioned before. So typical sub-transmission voltage level range from 33 kV to 132 kV, and capacitor banks or reactor banks are used to maintain the transmission line voltage. Okay, this is the figure of the electricity transmission system in Peninsular Malaysia. Okay, and then for the distribution system, we have two types of distribution, which are the primary and also the secondary distribution lines. So the primary distribution lines are ranging from 11 kV to 33 kV, while the secondary distribution lines are normally at 400 volt and 230 volt. So basically, these distribution systems come with both overhead and underground, same as the transmission system. Also have overhead and underground. Okay, next is the loads. So loads is divided into industrial, commercial, and residential. So very large industrial loads may be served directly from the transmission system. And basically for the industrial loads, mostly use the induction motors. While for the commercial and residential loads, the loads types is, for example, lighting, heating, and cooling. And then the greatest value of load during a 24 hours period is called the peak load or the maximum demand. Okay, this figure shows the electricity consumption, Malaysia electricity consumption in 2014 from the Malaysia Energy Commission. Okay, so Malaysia Energy Commission or Suruhanjaya Tenaga, which operated in January 2002, is responsible for regulating the energy sector in Malaysia in ensuring reliable electricity and gas supply at reasonable cost as required by all sectors such as industrial, commercial, transportation, communication, and residential. Okay. So, statistic that shown by Energy Commission indicated that Malaysia is among the highest in terms of consumption and intensity of energy per capita in Asia. Okay, the annual growth rate of Malaysia final energy consumption stands at 6% base for a 20 years period. Okay, if you look at here, this is the electricity consumption in Malaysia in 2014. So the total electricity consumption is about 121,689 gigawatt hour. So this 121,000 the percentage division of application that use this electricity consumption is from 44% is from the industry, 32% from the commercial, 21% is for domestic, 1.2% is from the public lighting, 0.3% from others including the agriculture, and 0.11% is from the mining. So the total is 100 to 21,000 gigawatt hours. Okay, this is the website, the official website of the Energy Commission. So as you can see here, starting on 1st of January 2008, Energy Commission has agreed to use the MSIEC 638-2006 IEC standard voltage as the nominal voltage for supply system, which is 230 for single phase and 400 volt for three phase, with range for plus 10% minus 6% at the frequency of 50 Hz range plus minus 1%. Okay. This is the table of the electricity tariffs for Tenaga Nasional Berhad effective from 1st of January 2014 until now. Okay, so the first one is you can see here for the first 200 kilowatt hours per month is around 21.80 cent per kilowatt and so on lah. Okay, next is the units of energy. Okay, units of energy. So the capacity of an agent to do work is known as its energy. Okay, so we have electrical energy and also electrical power. So electrical energy is the capacity to do work. The most important forms of energy are mechanical energy, electrical energy, and thermal energy. So for the electrical energy, the unit of electrical energy is joules, equivalent to watt seconds. Watt times seconds is joule. Okay, so joules is what you time with the seconds. Okay, and then we have the electrical power. So power is the rate at which work is performed or energy is transmitted. So unit of electrical power is watt, which is joules over seconds, we get watt. Okay, so joule is watt times seconds. So watt per second. So we can just cancel out, so we can get watts. Okay. So we look at the first example, example 1.1. How much energy does a 100 watt electric bulb consume in 2 hours? So we have here is the watt, is the power, and then this is the time, 2 hours. So 1 hour equivalent to 3,600 seconds. Okay. So if 2 hours equivalent to 7,200 seconds. So energy, as I mentioned before, is watt times with seconds. So this is watt, this one is the seconds. So because we use 2 hours, so it equivalent to 7,200 seconds. So you just times watt and seconds, you get 720 kilowatt second or 720 kilojoules. Okay, we look at the next example, which is example 1.2. So the vacuum cleaner with capacity 2000 watt, this one is the power, is used for 2 hours once a week. 2 hours once a week. Calculate the annual energy consumption of the vacuum cleaner or the yearly energy consumption. So for the solution, so vacuum cleaner it used 2 hours per day. Okay, and then if considering 2 hours once a week, in year is around 52 days per year. Okay, and then we have the P is 2000 watt. So the annual energy consumption of vacuum cleaner is you have to calculate 2 hours per day, you times with 52 days per year, and you times with the power. So this one is cancel out. So you'll get 208 kilowatt hours per year. Okay. And then if you want to change the units to joules, so this hour is 1 hour, so equivalent to 3,600 seconds. As we know that in joules is watt seconds, so you have to calculate, you have to times the value of watt with the seconds. Okay, so 208 kilowatt hour, we times with 3,600 seconds, you'll get 748 800 kilowatt seconds or 748 800 kilojoules. So next is about the efficiency. Okay, so efficiency okay, so energy is available in various forms from different natural sources such as pressure heat of water, chemical energy of fuels, nuclear energy of radioactive substances, etc. Okay, so all these forms of energy can be converted into electrical energy by the use of suitable arrangement. Okay, in this process of conversion, some energy is lost in the sense that is converted to a form different from electrical energy. Therefore, the output energy is less than the input energy. So the output energy we divided, okay, the output energy divided by the input energy, okay, output energy divided input energy is called energy efficiency or simply efficiency of the system. Okay, as power is the rate of energy flow, therefore efficiency may be expressed equally well as output power divided by input power. Okay, so we look at the first example, example 1.3. Energy is supplied to a DC generator at the rate of 4,200 joule per second. Okay, the generator delivers current I 32.2 ampere at 120 volt. So the question are, what is the percentage efficiency of the generator and how much energy is lost per minute of the operation? Okay, so this is the solution. Okay, the solution is, so first we have to know that the energy, the input power Pi equivalent to this one. Okay, this one is the Pi or the input power. So input power is 4,200 joules per second. So it is equivalent to 4,200 watts. Okay, joule second is watt. Okay. So input power is I times with T is V. Okay, P equals to IV. So or EI. So E is, this one is E or V. So 120 we times with the current 32.2 amps. So you get 3,864 watts. So first you have to find what is the efficiency, percentage of efficiency. So efficiency, as we know, the equation is output energy over input energy. So P output over Pi. So we know P output is 3,864. We divide it by 4,200 times with 100%. So we get the energy efficiency for the generator is 92%. Okay, next we have to calculate what is the energy loss per minute of operation. So power loss is PL equivalent to P input minus P output. 4,200 minus 3,864. So we got P loss is 336 watt. Okay, so energy loss per minute equivalent to 60 seconds. Okay, 1 minute equivalent to 60 seconds of operation. So equivalent to PL you times with T. So PL is power loss is 336. You times with 60 seconds. Then you can get 20,160 joule or 20,160 watt second. Okay, 20160 watt second. Okay, so note that efficiency is always less than 1% or 100%. So in other words, every system is less than 100% efficient. So this is the solution for example 1.3. Okay, finish with chapter 1. We'll continue with chapter 2. Thank you so much. Assalamualaikum warahmatullahi wabarakatuh.